let's look at the solution for this question. It is a very interesting question. It is rather a previous entrance examination question. Now this question can be solved by two different methods. Generally students follow two different methods depending upon the idea that strikes at that moment. Here let us see the solution for this question in both the methods. Now first of all, in this network as given, so this cell of 12 volts, which is an ideal cell because it is resistance less internal resistance is 0. Let us name it as E1 for our notation purpose, and this E1 is 12 volts, and this of EMF, let us say E2, which is of value 2 volts. Now let us say one of these two cells can be treated as a discharging cell, the other is a charging cell. It need not be a condition that all the cells to be discharging. So for our convenience, I am supposing this is the discharging cell deriving out, let us say, a current I into the circuit, and this current I here is finding at this junction two paths, and a current Ig has to go into this. But of course this galvanometer current is given 0. So the only current in this path now, everything now here is I, and here this is Ig. Of course it is 0 as indicated in our data, and so let's complete the circuit. Now the first method in our solution, it's a very simple direct solution because the current in this path is I and there is no potential drop in this path because Ig is 0. So we can make an equation, I into R should be equal to E2. There is no other potential drop being I into R should be equal to E2. This is possible only when Ig becomes 0. But the value of I, how can we get, is E1 divided by 500 plus R, EMF divided by total resistance. E1 divided by 500 plus R should give us I. That into R, that should be equated to E2. So if Ig, the current through this galvanometer, equal to 0, then the possible condition is E1 divided by 500 plus R into R. This is actually simply I into R, and this is equal to E2. Therefore, let's substitute the values. E1 is 12 divided by 500 plus R into R is equal to 2, and this simplifies, this implies so we arrive at the answer already. This is R equal to 100 ohms, that is option 2 is our correct answer. But sometimes we can solve this problem by another approach. We try to solve this problem by another approach. Rather, of course, it is I am going to use Kirchhoff's loop theorem. Of course, this we are going to study in detail in our next concept, Kirchhoff's laws. But taking all together now, let us show that solution also. So most of the students follow that method also in solving such a network questions. Our first idea will be Kirchhoff's laws. So this idea we may get or may not. So general procedure of Kirchhoff's law also let us discuss now. The second method is Kirchhoff's laws method. For this, as I told you, we have to use a loop theorem. So let us name it now, loop. This is A and this point is B and this point say C and this is D, E, F. Now let's take first the loop A, B, C, D, E, F, A. Now in the loop, in the closed loop, A, B, all along A, B, C, D, E, F, A. In this, if we apply Kirchhoff's second law, so this is, here you see, I into R, we are going through this resistor. Of course, we study this convention in our next concept, but here, in general, here you can come back and you can understand this, approach. This is minus IR, that is here now it is in this loop. I am going to write the total equation, minus I into 500 minus Ig into G, which is 0. Here we are going through this cell from positive to negative, minus 2. And here we are passing through this cell now from negative terminal to positive terminal. This is plus 12. So the algebraic sum of potential drops and EMFs in this closed loop must be equal to 0. And from this we get now, therefore, out of this I comes out to be 1 by 50 amperes. And now let's use the loop, the other loop, A, B, E, F, A. This loop let us take up now. So now in the closed loop, further in the closed loop, A, B, E, F, A, A, B, E, F, A, this closed loop. Now when we say this is minus I into 500 minus I into R, and the cell negative terminal to positive terminal, plus 12 equal to 0. Minus I into 500 minus IR, this is plus 12 equal to 0. Now if we substitute the value of I is equal to 1 by 50, now by using the value of I, we get R. In this we can substitute R is equal to 100 ohms. So you see, so of course the first one appears to be very simple method, but the idea of now equating the potential drop across this IR to E2, we may get, may not. If we get it, it's fine. We can solve it very easily, R equal to 100 ohms. Otherwise, if we were to solve by conventional method, general format, by using loop theorem, we can solve it by this method. So our answer is option 2, that is 100 ohms.